Hello everyone, welcome to this video. My name is Amir Senahrari. I'm a Google Earth Engine expert. In this tutorial, I'm going to show you how to calculate methane emission using Sentinel-5 data with monthly temporal frequency. In this tutorial, I'm going to show you how to convert data from the daily to monthly temporal coverage, and then how to do anomaly detection for the methane emissions in the Tehran, a metropolitan area in the Iran. And also I'm gonna show you how to do trend analysis using man-Kendall algorithm in the JavaScript code editor environment. This is a very useful tutorial regarding to Sentinel-5 data works in the Earth Engine platform. And all of the datas and also the techniques can be utilized for all around the world. Let's go to the code editor environment in the Google Earth Engine platform. In the first step, we need to identify the region of the interest. To do this, go to the search places and dataset and write about FAO administrative layers. 3 administrative layers available: country boundaries, first level and second level. The first level equals to province borders. Import it into the code and then throw the marker. As you can see in the drawing tools, you can select or choose your region of interest. For example, I'm gonna work on my location or region of interest that is here, Tehran. If you want to mark your region, throw the marker tools, select it first, and then we need to select the boundaries or the provinces that covering this area. It's very simple in the Earth Engine. Make a new variable as ROI equals to from table, or you can filter the table according to the marker. Throw the filter bounds. After this, using map.addLayer, throw the map.center object. You can have focus on the study area and through the map.addLayer, you can visualize the boundary of the region you are working. That's what it looks like now. In the next step, we need to call Sentinel-5 data in this environment. Make a new variable as Sentinel-5 equals, throw the search places on dataset, write here, for example, Sentinel-5. As you know, Sentinel-5 is a satellite specifically used for the air quality and air pollution and various air quality parameters estimated using this satellite data and already available in the Google Earth Engine platform. One of the applicable products about the methane produced by this data, and here you can find it. For example, if you add methane as the prefix here, you can see that the offline methane data available here. Import it as an image collection. It is CH4 offline data. As you can see, its description here is available. You can get more information in this regard. The dataset available since the February 2019, and also the other data information such as spatial resolution and band combinations available here. As you can see here in the new tab, through the bands mentioned, the spatial resolution is 1 kilometer, but I think it is wrong because in the data description mentioned, the spatial resolution is around 7 kilometer. And also when you visualize this data in the Google Earth Engine platform, you will notice that the spatial resolution is lower than 1 kilometer. And also I'm almost sure that the main spatial resolution is 7 kilometer. The main band we are going to work is CH4 data with the value range from this minimum to maximum and the unit mentioned here. And also everything is clear, and now I'm gonna make a monthly dataset from 2020 to 2024 and then show that how we can monitor methane variations in the region of the interest you are working. It's no matter I'm working on this region. The region of the interest is not important, and is not important. You can use this tutorial for all around the world, and because the data has a global coverage and daily available for all around the world. So here import assigning image collection to Sentinel-5, and then we need to define a period of time in which we are going to do our analysis. Through the dot filter date, define time start and time end. The time start here equals to 2020, and the end date equals to 2024. So we need to produce the from start and end date, the monthly variation from daily to monthly. We need to do a conversion in this regard. So then define the boundary of region through the filter bounds and bounds your data to the region of the interest that is created. So before go through the conversion, we need to select the band, the target band we are going to work with. In the bands, the band names should be copied and pasted into their brackets. As the band name is very long, you can make a new bracket and replace the new name and replace it with a new name. For example, the new name should be methane, like this, or CH4 for the simple analysis. As you know, CH4 is one of the greenhouse gases that its emission depends on agricultural activities, fossil fuels, and etc. So, and now we want to do some sort of monitoring and change detection regarding to methane emission over the regions we are selected. So, for the next step, we need to make a list for the years we have, from time start to the time end, because during this period of time, we need to make monthly data. A new variable is month list equals to Earth Engine .list.sequence, allowing to make a list according to the starting date to the ending date. But as you can see, the start and end date have a string format, and we need to change them from the string to the number. So here Earth Engine .number.parse is a function allowing to convert a string to a number value. Time start and then Earth Engine .number.parse again for the time end. As you can see here, we have, but this is the year list. It was my mistake. The year list here. Run the code, but the time end is not defined. Yes, time start and time end. Run the code, and as you can see, the years list created from 2020 to 2024. As you can see here, the last year equals to 2024. But when you call the data in the Earth Engine, the data, for example, here calling from the early 2020 to the late of 2023. So we need to remove 2024 from the list because we don't want to have doing some sort of analysis on the 2024's data. So that's why we need to remove or subtract the list from value number 1. After subtraction, you will see that we have 4 years from 2020 to 2023. For each year, we need to have 12 months. So then make a new variable month list equals to Earth Engine dot list dot sequence starting from 1 to 12 because we have 12 months for each year. If I print the month list, you will see we have a list of values starting from 1 ending to 12. So that's we did so far. For the next step, I need to make a loop, actually an integrated loop from years and months to filter Sentinel-5 data according to each year and each input months. It's very simple things. So here we want to make monthly methane product, methane monthly, just like that, equals to, first make a loop based on the years list from year list dot map. Map is a function allowing to make a loop over input elements. Dot map, make a new function inside the map, and each input year named as a year. Then we need to make another loop here. Return month list dot map again. This is the second loop creating inside the first or year list dot map a new function. This time the input is month and the name for each input in the function should be month. So in the body, now we need to filter Sentinel-5 images according to the year and months that imported through the loop. So make a new variable as monthly equals to, so get Sentinel-5 data first and then through the filter make Earth Engine filter calendar range. Two different calendar range needed, one for year and one for month. In the next line should be better. Each calendar range including 3 arguments: starting date, ending date, and also the field. The start date or the start value is about the year because we need to filter our data first based on the input years, and then the field should be year. Then another calendar range needed, filter calendar range. Then for each year we need to filter data based on each input month, just like that. And finally, after the data filtered based on the year and month, you can get the average through means here. It's very simple technique. So in the next step, as we are making a new product in the Earth engine, we need to make a new system time start to justify the new acquisition date or or we need to define a new system time start that defined or justify the new temporal resolution for the data. So here make a new variable as date Earth engine.date from year, month and day. Some couple of arguments available here. The year equals to the year, month equals to the months, and day should be 1. And get rid of time zone next. So here. Finally, the function returning the monthly data that is created with new properties. To add new properties, .set allowing us to make new properties variable. So the new property is a new system time start that equals to the date with millisecond, with millisecond format. As you know, and as I pointed out in the previous tutorials in the Google Earth Engine platform, Earth Engine explaining the dates and temporal information according to the millisecond format. That's why Google Earth Engine works. So, after set a new system time start, we need to have a new system index. .set, I'm making a new system index. System index equals to, so the system index should be explain or equals to the date information, date, but this time we need to see the dates with the date format, year and months. Now I'm converting the date information to a string format through that format, and I want to see the date with this format, years, month and day, but no need to add the day. If you want to add it, it's very simple to add double D here. So the monthly product now is created. Through the print, you can see the Methane monthly data. A new list is under computing. This is a list because the input for the functions are the year list and the month list, and the output will be briefly listed in the 4 different elements, and each element including 12 elements separately. As you remember, we had 4 years, now we have 4 elements. For each years or each element, we had 12 months, that is here 12 elements in each sublist separately. So what we need here is to convert the list from nested structure to the integrated structure. So here through that flatten, we can convert the nested list into the integrated one. Run the code again. A new list created with 48 elements starting from the first date, as you can see, from the January 2020 and ending to the last date, December 2023. That's what it looks like. But still we have a problem. If we want to do next analysis on this image collection, we need to convert it from the list structure to the image collection format. Just add Earth Engine.image collection. It's very simple. That image collection, and close the parentheses and run the code. Finally, we will have a new image collection with 48 bands. In each date, one monthly product as Methane available with the time start and index information. That could be useful for the next step processing. So, after monthly product is created, we can actually plot the monthly methane variation over the province. So here, just throw the print, make a new interface as chart image.series. So input image collection, instead of image collection, we will have monthly methane. And instead of the region, we need to have the region of the interest. Through the reducer, you can get any statistical operation for the region of interest. If you need to get minimum, maximum, the average, median, or a standard deviation, reducers helps. So here, Earth Engine.reducer, I want to have the average value for the region of interest, and a scale equals to 7,000 or 7 kilometer, and X property equals to system time start. Just like that, save your code and run it again to see the monthly variation for the region of interest. A new chart is generating. As you can see here, the monthly variation showing an increasing trend in the methane values. Some of the months higher values and some of the months lower values. High values in the methane plots actually showing that we had higher emissions in the greenhouse gases such as methane because of the fossil fuels, because of the agricultural activities, and also there are several other reasons that could increase in the methane gases into the atmosphere. But unfortunately, in this region, a decreasing trend detected that starting from this value and ending to this range over the 4 years. That needs more analysis to identify when we had higher values and when we had lower values. To get a better understanding about the variation, anomaly detection could be very helpful to see that when the methane emission gets above the average and when the methane emission dropped to below average. This is a very important thing that we can identify through the actually anomaly detection in the Earth Engine platform. So make a new variable for the average. For example, here we have average variable equals to from methane monthly. I need to calculate the average of each pixel value over the time period from the monthly format. So once the average created through the map.add layer, you can have a visual overview on the data you are created and you are working to see the spatial pattern of the methane monthly in your region of interest. The average image clipped based on the ROI, and then for the visualization, go to the data description here, open it into a new image page, a new tab, and then there is an example code for the visualization. Just copy and paste it, just like that. Copy and paste it into your code. Here we have band visualization. The values ranges from 1900 to 1750, showing very well with this specific color palette that's used for the methane visualization. So here, instead of visualization parameter, you will have band visualization, and the layer setting or the layer name in the layer setting should be methane average, and use the false to avoid automatic visualization. So save your code and run it again. We have methane monthly. There is a problem. I think one letter missed here. Now code working very well. We have the average image and waiting to see the visual characteristic of the product we created. The image is loading. So we have there is a problem in the contrast, but you can solve it through the stretching technique in the layer setting. Go to the layer setting first, and then through the stretching tools, use 90% stretch to increase the contrast. Lower values, darker color, and higher values or higher emission, brighter colors. For example, the regions with red showing higher emission, and regions with dark blue showing the lower emissions. Apply and wait until the final product visualized. As you can see here, the regions in which carbon emitted, in the regions in which methane emitted highly, showing with the red and yellow colors, and the regions with no emissions masked from the product and also or showing with the darker colors, as you can see. If you have more zoom in, or if you scroll down on your region of interest, you will see that the pixel coverage, a large area, the pixels covering large area on the surface on the Earth's surface, and also it sounds like 7-kilometer product rather than 1 kilometer, as I pointed out earlier in this tutorial. That's what it looks like, and image is visualizing. In the regions, we have a metropolitan area. In the metropolitan region, Tehran, as you can see, more methane producing. As you can see here, we have more fossil fuels, we have more agricultural activities in these regions, and you will see that the more values recorded. That's what it looks like. But in the mountainous regions in the north, as there is no agricultural activities and no detectable fossil fuels, you can see that no value is recorded in this region. So in the next step, I'm gonna calculate the difference between the methane emission for each date, calculate the difference between the methane emission in each date and the average image. That could make a good insight about the methane variations or the methane risk in different dates. So here a new variable as anomaly created equals to get methane monthly first, and then make a loop in which each input image consider it as IMG, and then the index or anomaly index equals to the difference between image of each date and that subtract the average image that is created. Rename it as anomaly and the code returning the index. So with the properties of input images, specifically system time start and system index. So after anomaly image created, print it to see how it works and to see if there is any syntax problem in the code or not. A new image collection under computing, and here we have 48 elements again, but this time each band showing the anomaly or the difference between the methane and average over the period of time we are working. So making a new print to chart the variations. User interface, chart image.series. Instead of image collection, we have anomaly, replace region with ROI, and as I'm going to get the average anomaly variation in the region of interest, I'm doing a spatial aggregation based on reducer mean. Reducer dot mean, just like that, and the scale should be equals to 7 kilometer and X property equals to system time start. Run the code and a new chart is creating. A new chart is creating to see the anomaly variations. The same trend created, but the difference is the range of values. The negative values showing that the methane emission is lower than a long-term average, and also the higher values or the positive values showing the dates in which the methane emission is higher than the actually normal average that we have. So in order to have a better visualization, I can change the chart style or the chart type from the linear chart to from the line chart to column chart. We can do it through the set chart types. Make a bigger space for the code, and the column chart is a new chart we are creating. It is generating in the right panel. You will see the same values, but with the better difference, with the clearer contrast between the positive and negative dates. So as you can see, for example, November 1st, 2021, the rate of anomaly was higher than the long-term average. And also these dates are, we can call these days or call these months as the methane risk dates that's increasing, that in which the rate of methane emission increased a lot beyond the long-term average, that can make concerning for the regarding to the greenhouse gases and also for the people living in that region. And as you can see, the frequency of the positive values clearly increased over the last 5 years. So if you want to have the positive years, positive months as a separate variable, we can make a new function to calculate the average value for each month and filter the values or filter the months in which the methane emission is far from the long-term average. So it's very simple technique. For example, here I'm gonna make a single variable that only showing the positive values or positive months, and I'm going to get rid of the negative months in the anomaly variable I have created. So here a new variable as positive anomaly created equals to get from anomaly images first, then make a new function, throw a loop, and each input calling as img. So then we need to do some sort of calculation here. The first we need to calculate the average of anomaly over the region of interest. So a new variable as average anomaly equals to, so each input get the input image as an img, and then through the reduce region you will be able to calculate the average value for each date. So the first argument is the average reducer dot mean, and the second one is the geometry equals to the ROI, and the third is scale, and the scale should be around as this data have 7 kilometer spatial resolution, the scale should be 7 kilometer or 7,000 meter. So to get it as a value, add dot values and get the first value, that gets the first value in this dataset. So to convert it as a number from a value to a number, Earth engine.number can be useful. So now function returning the anomaly image as an img, and then with the properties of input images. But we need to append or actually attach the average value for each image as a new property to the anomaly values returning. Make a new property dot set through set function. The new property is methane value, and then set normal value to the methane value as a new property. Print positive anomaly and see the result in the right panel. A same image collection returned as we had regarding to the anomaly. The only thing changed here is about the properties. We have a new properties showing the value, the average anomaly value over the province. So now I can make a filter to filter the data based on the average value. It's very simple. For example, here that filter, I'm going to use only positive anomaly values for the further analysis. That filter, the new property is methane value, and but before that we need to define the filter, Earth engine.filter.gt greater than. I need those of images in which methane value is greater than 0. Run the code again. This time we will have a new image collection with the new images. Only 23 elements remained. 23 elements in which the anomaly value, the average of anomaly is positive. As you can see, all of these images including positive anomaly values. We can make a new plot based on. Just copy and paste the previous plot, but this time only we are using the positive anomalies for the same region. A new chart is creating. And as you can see, here we have only those of months in which the anomaly average is positive. And also we can save their images using export.image to drive to. You have their trends, their changes, their plots, and also you can save their rasters if you need. This is a simple actually example about the query and making queries in the Google Earth Engine through the properties we make. For example, here through the export image to drive, I can get the export from positive anomaly images. So the input argument is image equals to positive anomalies, make a layer stack through the .to bands, and then clip it based on the region of interest. The name of output description is positive anomaly, and then the region of interest ROI, the scale of output 7 km, maximum pixel in each frame 1E13, and then the next is the output folder is the test, or you can use any other folder you have in your Google Drive. So, and the CRS coordinate system equals to EPSG 4326. This is WGS84 code that you can use this CRS for all around the world. So save your code and run it again. This time go to the task, and after a few moments you will have a new task here. Click on run to start the process of saving into your Google Drive. Run it, and after a few seconds or a few minutes you can have access to the output through your Google Drive. So back to the programming steps. So until now you learned how to deal with the Sentinel-5 Methane product, and also we showed you how to convert it from daily to monthly format, how to visualize it, how to plot it, and how to see and find the anomalies and how to get the queries. And now from a spatial point of view, I need to show you how to do trend analysis in the spatial from the spatial field of view. We need to see that in which pixels the methane value increases and in which pixels the methane value decreases over the period of time we are working. So it is also very simple technique in the Google Earth Engine platform. Make a bigger space for the rest of scripts. Make a new variable as trend equals to get monthly methane, or the methane monthly images. Methane monthly is available, and now I'm gonna reduce it. I'm gonna calculate the trend through the Kendall correlation. Earth Engine.reducer Kendall correlation is available here. So print the trend. In the right panel, the new image created. This image including the gain or a slope of changes for each pixel during the time period. We have two elements, methane tau and methane p-value. The tau is the slope of changes here. And now I'm making a new, I'm gonna visualize the tau image. Map.add layer, visualize the trend, dot select tau band, methane tau, and then clip it based on the region of interest. And for the visualizations, I just use the palette we had for the visualization process and skip the minimum and maximum value. So here we have a palette. The layer name is CH4 trend or methane trend, and use the false to avoid automatic visualization. So save the code and run it again. As you can see, the new trend image created. Here we have CH4 trend. Check it on and wait until the final result visualized. And also here, if you go to the task, the positive anomaly bands is available to download, and you can download it through the opening drive from your Google Drive. So back to the trend image. CH4 is created and visualizing. To increase the contrast for the visualization, you can go to the stretching method as it is pointed out earlier in this tutorial. Through the 90% enhancement or other enhancement technique, you will be able to increase the contrast in the image. So stretch by 90%. After new value applied to the ranges, we can use the apply to see the new visual characteristic. Apply it again. It's a little time consuming process compared to the rest of the script we made. For the trend analysis, as we have a lower range of values, I'm suggesting to use actually limited a number of colors. For example, here we can use only 3 colors, starting from green for lower values, black for the values with with no significant changes, and also the red for those of pixels with higher changes. Click on CH4 again, go to the layer setting and increase the contrast. This is the final image, but we need to increase the contrast through the layer setting here. The values ranges from -1 to +1, and I'm increasing the contrast by 90% increase. And then apply the new range of values. In the final image, we have 3 colors. The red showing increasing trend, and also black showing the no significant change, and the green showing the lower lower methane emission or lower trend or negative trend. Through the inspector, you can see or check the values for each pixel. The positive values showing increasing trend, and also the negative values showing the decreasing trend. CH4 trend is creating. Yes, this is 0.1 that's showing increasing trend. But here, if I click a new pixel, I'm waiting to see the result, and same time, this is -1 that's showing a decreasing trend, a significant decreasing trend. I changed the stretching technique and applied to see the new visual properties. Now we have a better contrast. Through the other methods, you can have a better contrast to differentiate the increasing and decreasing trend in the pixels. Then apply. Yes, now it's better looks like. For example, this region with the red color, waiting to see the value. As you can see, it is 0.3. But visualization process is a little tricky, and I highly suggest you to check the pixel values when you are using enhancement technique. For example, as you can see, the minimum range of values is really close to 0. And also it is possible to see some sort of darker pixels with the values near to the, for example, values above the 0. And also that might be a tricky to only actually trust to the colors into the Google Earth Engine, and I'm highly suggesting to use the inspection tools available in the Earth Engine to make a conclusion about the status of each pixel. As you can see, it is 0.1, and also it is still showing an increasing values. So if you want to have a more realistic overview, would be better to use 90% stretch or 90%, because the range of values is more realistic in this case. And the values you checked or inspect is really close to see what your eyes watching in the region of interest. So as you can see, in the most of the regions we have an increasing value regarding to the methane situation. I hope you like this tutorial and you can use this tutorial for the rest of the areas you are working. If you had any problem and if you have any questions regarding this tutorial, please put your comment in my YouTube channels. And also I will share you my code, and also it is available below this video in the description box in my YouTube channel. If you had any problem into your code, first compare yours with mine, and if it doesn't solve again, and also if a problem still exists, you can reach me out in my YouTube channel and throw the comments, and I will help you to solve the issues regarding this tutorial. Thank you for your attention.